All right. Hey, everybody. So, right now we'll start solving the silver contest for December 2021. Bronze was a lot harder than I expected, a lot harder than I remembered it. So, you know, hopefully I could solve the silver contest still, but in either case, I'm just gonna try my best to do the best I can in this contest to kind of explain my thought process along the way also. So yeah, let's get started. All right. Okay. So first let's look at the problems, kind of get an idea of what they are, and then I will try to see which one I like best and what I'll approach the best. So it's a long patch of farm along a highway. That's like a one-dimensional number line. Okay, I like that. There's K grassy patches. Each patch is located at position P of I and associated tastiness value. I see. Farmer Noj has situated his cows at locations F1 and FM. Okay. I see. So farmer needs to pick n locations, not necessarily just for his cows to be located. These just be distinct from the occupied by cow nodes, but it's possible for Farmer John to place his cows at the same locations as grassy patches. Okay. Whenever a farmer owns, so this is, I need to keep this in mind, not necessarily integers. Whenever a farmer owns a cow close to a grassy patch, he can claim ownership of the patch. If there are two cows from rival farmers equally close to the patch, then farmer Node claims the patch. Given the location farmer Node's cows and location tasting all the grass patches determine maximum total tastiness farmer John's cow can claim. Okay, do I have like less cows than farmer Noj has? Oh, I see. Okay, so I have K, M, and N, where N might be like less than K. So that's the hard part. Yeah. All right. Well, this is interesting. We'll keep this in the back burner. We might look at this one. Let's look at this problem. N fields containing the through M. Between these fields are M directed paths. So this is a graph problem. A farm contains two barns, one in field one field N. You want to ensure that there's a way to walk between two barns along some series of paths. So you want to build up to two new paths to accomplish this goal. Due to the way the farm is situated, the cost of building a new path is I minus J squared. Okay. Minus J squared. I see. Okay. This is interesting. T sub cases quickly. Oh, okay. This is weird. I don't know how I feel about this. USACO's never done this before, but I guess this is just making their input cases more robust because they can fit more of them in. Oh yeah, this is a cool graph problem. I think this might be interesting too. But yeah, this seems cool. All right, let's look at the last one, convoluted intervals. There's a set of n intervals where ith interval starts position A of I and ends at position B of I. Okay. So LC, this is important for this problem. Bessie chooses an interval, LC chooses an interval, right? And LC's interval could be the same as Bessie's. Given some value K, they win if AI plus AJ. This is weird to parse. Let's think about what this means, right? Oh, okay. There might be a better way to think about this. Yeah, this is interesting. Okay, so this is a weird problem. I think it all comes down to finding a better way to represent this. Because you can't, there's 10 to the fifth intervals. You can't just iterate through every K and then every ordered pair. That's too slow. So we want to ideally be a lot better than that. Okay, this is a cool problem as well. I think the most straightforward problem in this set and the easiest to do, it's not this one. I just want to take a look at this one. Okay, this one's going to be the weirdest, I think. This one's the one I have trouble with the most. So I might say this one for last, but this one seems a little bit doable. It's like a graph problem, right? So I think for graph problems, the good rule of thumb is to draw it out. So let's draw out an input example. So there's two sub cases. In and M, and then two lines of input, 5, 3. Okay. So the first input, let's just do the first one, the second one. The first one has 5 nodes and then 2 edges. So there's 1. Ooh, that's a really weird color. It's very bright. One, 2, 3. Wait, hold on. 1, 2, 4, 5. Okay. So 1 is an edge to 2, and then 4 is an edge to 5, like this, right? Yeah, I think the best way to do this problem, right, is to build this edge. Can you build up to 2? Up to 2 new paths to accomplish this goal. Okay. So you build up to 2, and you want to kind of make this connection. So if we build this connection, it costs 4. So is that the answer? Huh, that's not the answer. Let me think. Is this wrong? Wait, so you have 2 barns, one in field 1, one in field N. You want to accomplish this way to walk between 2 barns. So you want there to be a path between 1 and N. Build up to 2 new paths. Oh, I see. You can build 2 new paths. So this is not the most straightforward way to do this. This is not optimal. The optimal one is to go here to here and then here to here, right? Yeah. Okay. That's interesting. Okay. And then for the other case, 1, 2, 2, 3, 4, 5. 1, 2, 2, 3, 4, 5. So there's already edges that look like this, and then you want to build this edge kind of, right? I see. Okay. Well, I mean, the way I can think of doing this is like, okay, so if you have a graph, right? Just put a bunch of nodes. I'm going to abstract this a little bit. So instead of having numbers and caring about what the numbers are, we just have maybe this is what the components look like, right? We have some components that exist already, right? So this is component. This is the starting component, maybe like 1's here, right? This maybe ends here. So this is the ending component. These are some intermediate components, right? So if I want to make a new edge, I'm never going to put it inside a component because that's just going to be redundant. Like I would never put an edge here. This would never be a new edge. This would accomplish nothing, right? So all the edges go from components to other components. So let me just make these really big super nodes. These are components, right, in the graph that are kind of isolated from each other. So my path goes from number 1, like the starting component, to another component, and then from that component to my end component, right? Or I can make a path just go straight from here to here. Yeah. Let me think. Is that always optimal to do that? I think so. So there's just 2. So you can think of the graph as this, right? There's the components in the graph like this. All these are some nodes that are connected, right? Maybe it looks like this. Maybe it's like a node by itself too as its own component, right? So maybe the end node is here and the start node is here, right? So like 1's on this one and like ends on this one, right? So this is the target one. To query the distance between, let me think. We want to quickly be able to, we want to kind of be able to get the distance from this starting component to every other component in the graph. Like that's what our goal is, right? And then also get the distance from the end component to every other node in the graph, right? Because if we do that, then we're able to kind of just find the node with the smallest end distance plus start distance, right? Let's think. How can we do that? Well, there's one way to do that. So let's look at the case first of like start component, right? So maybe we have this many nodes of start component. To find, let's take a node J, like some other node, right? To find the distance between it's the minimum distance between any node in here to any node to node J, right? Sorry, this is at most 2 barns, I think. Build up to 2 paths. Okay. So in order to find the distance, we kind of need to find the node in here that's closest to J, right? How can we easily do that? We want to be able to answer this question because the final solution is going to be like, here's the end component, here's the start. This is start, this is end, right? Because node n might be here, node 1 might be here. The best path goes from, oh, I see, hold on. Yeah, it goes from a node in the start component to J, maybe to another node in J's component, and then to end, right? So for every node, if we have the distance from start, we can kind of, for every component, right, calculate the distance from start. And then for every component, you calculate the distance to end, right? So we can find the best intermediate component to use. It's really hard for us to calculate what the distance is naively, and I'll show you why that's true. So the simplest O of n squared solution, right? For every node J, in order to compute this query, you try every node in S and you look at the distance between that node and J, right? And then you take the minimum, but that's really slow because that's O of like, this is maybe n nodes in here and there's n other nodes J we have to try. So it might be really slow. It might be like O of n squared, which is too much for this problem of like 10 to the 5th, right? Are there like 20 input cases? Jeez, this is gonna be I might do this in C++ because Java is very slow for like these input cases. So we'll see. Yeah. So that's that. So that's a little bit slow. We want a quick way to query like what the closest distance node is from node J, right? That's in the ith component. So if we look at all these nodes, right? In order, let's say this is a list from 1 through n, right? Here are nodes in J. And I guess these are nodes in the starting component that we have to query from, right? So for every node here, we want ideally like the closest node in the start component, closest to it. We could calculate this with a for loop, but I wonder if there's a better way to do this. I think it's the closest thing. Okay, so I guess we kind of almost have an algorithm now, right? First, step 1. We want to, for every node, get the component it's in. So every node has a component ID, right? So, oh wait, hold on. Let me erase that. Every node has a component that it's in, right? We will use a DFS to do this. Like this is the same thing as like the, this is like a DFS problem. We'll use the DFS to kind of do this, right? For every node, get the component that it's in, right? Then for every node, get the nearest distance, to start component and nearest dist to end component, right? For every node, you get the nearest distance to start, nearest distance to end, right? And then you have to do for every component, you need dist to start and dist to end, right? And you take the max, the minimum over, the minimum over every component, and that's your final answer, right? So to run this algorithm on the input case, let's do this one right here. So 1, 2 are connected, 4, 5 are connected, right? You kind of use DFS to say, okay, for a component, let's look at this table. So this is 1, 2, 3, 4, 5, right? Maybe this is component 0. Maybe this is component 1, this is component 2, right? So these are a component, this is a component, this is a component, right? For this one, the closest distance, so D to S is distance to start, right? The closest node for 1 is itself, so this is 0. The closest node for 2 is itself is 0, right? For 3, the closest node to start is this 2, which is distance of 1. For 4, the closest one is 2, which is distance of 4. For 5, the closest one is 2, distance of 9, right? And then this is D2 end. So for D2 end, it's so 1, the distance to end is 9 because you have to go from 1 to 4. From 2, it's 4 because you go from 2 to 4. And then from 3, it's 1 because 1 to 4. And then from 4, it's 0. For 5, it's 0, right? Now for every component, you also get the nearest D2 start. So for a component 0, the nearest D2 start is, I guess we'll call this like C to start. So 0, 1, 2, C to start. This is like the distance from component to start. So C to end, right? So for component 0, C to start is 0 because out of all the things component 0, the D2S is like 0. And then C to end of 0 is 4 because you look at the smallest one, right? For 1, D2 start is 1 and D2 end is 1. And then for 4 and 5, for the component 2, it's going to be 4 and then 0, right? And then we add these up. This is 4, this is 2, this is 4. So our answer will be 2, right? So that's kind of how this algorithm works. To get the component labels, to get this, right? You need to get the component label, you need to use, I think you need to use like, I think to get the component label, you need to use, oh shoot, hold on, okay. To get the component label, you need to use a DFS to just get this information. That's easy, right? D2 start, D2 end is a little bit hard, and then we'll show you how to do that. And once we get D2 start, D2 end, this stuff is really easy to get to, right? Because it's just the component wise, like minimum of these. So how to get D2 start? Well, what I'll do is I'll actually do this, right? 1, 2, 3, 4, 5. Maybe there's a lot of nodes, 7, 8, right? Maybe these are the nodes in the start component. 1, 2, 4, 7, right? I'm gonna compute 2 passes, a left pass and a right pass, right? So basically, on the left pass, what I'll do is the following, right? I'll say, I'll find the closest start node that's to the left of our node. So for 1 right now, there's no node to the left of it. There's no node to the left of it. So I'll say the D2 start of this is equal to infinity, right? For 2, we can use 1, so it's equal to 1. And then you update this to be 2. And then for 3, you use 2, so it's 1. For 4, there's no node to the left. Oh, actually, for 1, you'd use itself, so you'd say 0. For 2, you'd actually use itself and say 0. For 3, use 1. For 4, it would be 0 because it's itself. 5, it would be 1. 6 would be 4, actually, because it's 2 squared, right? 7 would be itself, so 0. So 8 would be 1, right? And then on the backwards pass, you go 8 is infinity because there's no node to the right. 7 would be 0. 6 would be 1. 5 would be 4. 4 would be 0. 3 would be 1 again. 2 would be 0. 1 would be 0. And you take the minimum of these. So 0, 0, 1, 0, 1, 1, 0, 1. So this is the D2 start. Like, all right, for this graph. That's kind of how you do it. I think it'll be more clear when I code, but yeah, let's just move on with it and just start coding. I think I'm gonna use because I don't want to use Java for this actually. I don't have C++ on Visual Studio, so is it this? Like, is coming up right? No. Sorry, give me a sec. I just need to figure out where the coding thing is. Syscam.com. Okay. All right, hold on. Give me a second to sign into this. This is a good compiler online for if you don't want to download your own C++ compiler. But all right, I think this will work. Okay. All right, sorry about that. Hold on, let me get this here. All right, so std include what does this include? It's how does this work? It's this thing right here. This is like important to include too. I think I'm sure. I'm really not the best at C++. I think everything else is good. Okay. There's just good imports to have. Okay. So now let's just do this code. So first is sorry. And T. What is it? TNM. Okay, TNM. And then vector of int vector. Oh, it's vector of int array. Jeez, do I remember C++ syntax enough to do this? C++ array syntax. Okay, so it's like this vector int graph array like that, yeah. And then you put the length of it in the okay. So I'll just do this. Yeah. TNM CNT. Jeez, I'm like praying this works enough. Let me just try for int test equals 0, test is less than t, test plus plus. Print. Wait, cout test, right? Let me just do this because I want to kind of start making sure like my understanding of the input's correct. This is really slow today. Is it really that bad? Okay, estimated queue time is 9 seconds. Oh, I guess because it's USACO, everyone's on this thing, maybe. Hello? 8 seconds. Jeez, okay, maybe I should go somewhere else and not use this. How easy is it to set up? Sorry, let me see if let me just see if it's easy to set up C++. All right, I'll set up my environment real quick and then I will finish the rest of this contest with you guys. I have 4 hours, plenty of time, so I should have enough time. All right, sorry about that. So this is taking me too long. I'll use just Java because um we should be fine with Java. Alrighty. Okay, so import java.io.asterisk java.util.asterisk void class problem one static void util one main string args. All right, so it's gonna be a little bit weird, but I'll have to use buffered reader. New input stream reader in, or it's not in, right? Okay, okay, cool. Got it, okay. So forget about this. This is annoying. Forget about this. All right, okay, let's just get started. Okay, so int t equals int, I think I do this, right? In dot read line. In dot read line will give me an, does this work? Oh, sorry. Integer dot parse int. That's how you do it. You can't just cast. That's not the correct way to do this. What is this? Int dot read line, does that work? Oh, so just do this. Cool. Zero is less than t. Oh no, I don't want to use I here. I'll use I for some of my other loops. Test equals 0. Test is less than t. Test plus. Okay. And then print test just to test if this works. Let's just, because it's first time I think using. Oh, sorry, this is also from. It's my first time using buffered reader, so hopefully I understand the syntax correctly. One. Okay, 0. Cool. Okay, this works. And string line equals int dot read line, and then spaces. This is, you guys should know this on top of your head. I just haven't coded in a while. Can I do that? Split? Yeah, okay, nice. I didn't even know they could do that. Okay. String array, okay. String array imp. I guess I could just do the string array imp equals string dot split. Okay, does that work? Oh, I see how this works. Okay. And dot read line dot split, and then we'll split based on spaces. How about that? Should work, right? What's wrong with this? Does this work? It's the error message I'm getting. Oh, sorry. Like that, right? That should work. Okay, cool. And it's the most painful input ever. Equals imp at 0. So integer.parseInt. And then int m equals integer.parseInt imp at 1. This is like the worst. Okay, graph. Okay, this is array list of integer array graph equals, this is new array list of integer array of size n, and then we'll do for int I equals 0 is less than I plus. Graph of I equals new array list of integer, and this is not allowed, so I can just do this. Okay, this is gonna throw an error. What is this? That's fine. I got this when I was competing too, so it's harmless. All right, for int I equals 0, I is less than m, I plus plus. The input should be the most annoying part, so hopefully we can get that out of the way. We'll just do this. I guess we'll just do int a equals 0 dot parse int imp of 0, and then int b equals integer dot parse int imp of 1. Okay, and then we'll do graph of a dot add b. It's bidirectional. I do graph of b dot add a. Yes, we're done with the input, right? That's it. Thank God. Okay, that was really rough. Okay, so now let's actually write the code for DFSing. We'll make a method that's public static not void. What about, yeah, I think void actually works. Public static void. We'll call this color, because what we want to do is to get the components, we almost want to, like, if we have a node 1 that's connected to all these nodes here, we almost want to like color all this like one color. Like if you think of a coloring book, you want to color all this one color, you want to color all of this like another color, and then this component maybe has its own separate color as well, right? So this is kind of like coloring on a graph. So that's why I'm going to call this method color, right? It takes in the graph. I think this is passed by reference, so it'll actually modify it. It takes in the list, right? Color, and it takes in oh wait, I have to do this. Hold on. Array list of integer, array list. I'll just do array list of, yeah, integer array graph. Can I do that? That's not how you do this. Is it just not recognizing it? Oh, sorry. Is it? Okay. So this works. Okay. And then we'll do int array color. Int. This is like, I'll call this C, the specific color we're using, right? And then we'll do int a. We also need a Boolean array scene. You know what? I don't like. I'll just do what I usually do, which is okay. Public. I think I just static enough. Static array list of static int nm, static array list of integer array graph, static. What is wrong with this? Oh, static. What else do we need to do? Static. We need int array color, static Boolean array scene, and then yeah, that's it. Okay, so now our method only takes in int a and c. All right, this is gonna save us a lot of time. Graph. I'll just do that. Graph of I like that. Perfect. All right, and this should be not int m. It should work like the following, like this. All right, okay. And then I will make this, put this method here. Sorry, that's messing me up. All right, okay, here we go. So now we have to fill out scene and color. So scene equals new Boolean array and color equals new Boolean array. And what is this color of the, oh, never mind, okay, fix itself. Enter, and then we'll do this. Ooh, okay, color, okay. So first we need to color the component containing the first, what I actually like to do is the following. I just like to subtract 1 from it, so it's 0 indexed. After 0 indexing everything, I want to color the starting node and color the component starting node to kind of check to see if there's like a trivial solution. So for instance, right? For int I equals 0, I is less than I plus plus. Color of I equals -1. Actually, we don't need to use a scene array if we can set this, because this kind of tells us that we've not seen a node yet. So again, color. So scene we can get rid of here. Yeah. All right, and then we'll do color algo. We'll call this color algo just to avoid naming the same thing. We'll run color algo on the starting node with color 0. So this would be 0, 0, right? If color of, what's it called? The last node. So if we're trying to get to n, right, which is now n-1. So if color of n is equal to 0, so if n is in the same component as starting node, print line 0, that's the answer, because so else this is when we actually have to do stuff, okay? A equals 1, I is less than. I guess we'll actually do this. So if they're not in the same component, what I'll do is I'll color algo 1. So n-1, 1. So this will do is I'll color the component n-1 with color 1. So now I know that color 0 represents starting, 1 represents end, ending. So now for int, so now I'll start my colors at 2 for int I equals 0, I is less than n, I plus plus. I guess we'll do I equals 1, I is less than. I guess no, this is fine too. If color, oh, didn't see. If color of I is not equal to -1. So if, oh, actually is equal to -1. So if we haven't color node before, we want to start a new coloring, right? So we want to run color algo on I with color C, and then we want to do C++, right? And what this does is it colors the current graph that color you want it to do. So what we also have to fill out this color algo method, right? If color of A does not equal to -1, return. So we don't do anything, right? So if it's not empty, otherwise color of A is equal to C, and then for B, for int B in graph of A. So for every child in graph of A, color algo B and then C. I think this actually just does it. This colors the entire graph. So after this point, right, the entire graph should be colored. Now we have to do populate B. What is it? What do we call this initially? D2E and D2S. D2S, populate D2. What is this? Populate D2S, populate D2 end, populate C2S, populate C2 end, right? So for D2S, here's how I'll do it. It's in 2 loops. So for int I equals 0, I is less than n, I plus plus, right? We'll set the distance, we'll set the int prev. So just looking at the algorithm we did earlier, like trying to code that up, we'll start int prev equal to negative big number. Or this is way too big actually. Maybe we'll just do this negative, yeah, that's good enough, yeah. So if color of I is equal to, what color do we say? 0, right, for start. If color equals 0, so if it's a starting vertex, we set prev equal to I, right? And now we're able to do this. Oh, we actually have to initialize this array. Int array D2S is equal to new int array n for int I equals, oh, it's a long array actually, because these distances could be really long. I think they even say in the thing. Yeah, this is kind of tricky. This might be really big, so you have to be careful. You have to use longs here. Long array. I equals 0, I is less than n, I plus plus, and then D2S of I should be equal to long dot. Actually, we'll just do 10 E10. Can you do that? No, I can't do that. 10, 10, is that allowed? No, it's not allowed. Okay. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Does that work? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Oh, it's erroring because this is trying to make it int. Okay. We'll just do is equal to long dot max value. Yeah, how about that? Oh, that's how you do it. Okay, cool. D2S of I is equal to math.min of D2S of I, and then I minus prev, so this amount, times I minus prev. Except we have to be careful because this needs to be a long, and this needs to be a long. So let's do that. Just do that, yeah. Hopefully this avoids overflow. We'll see though. So that's how you do the first pass, right? Then you have to do the other pass. So I equal to n minus 1, I is greater than or equal to 0, I minus minus, so this is the negative direction pass, 200,000. We don't have to make a new int. If color of I equals 0, prev equal to I, otherwise D2S is, now it's not I minus prev, it's prev minus I, because now prev is in front of I. Okay, so this is for D2S. For D2E end, it's very simple. So it's take the code, copy paste it. This should be an E instead, because this is the end, right? Prev, you don't have to reset. You don't have to reinitialize. This is D2E. All of these should be D2E, actually. Let me just go through and change it. This is a part I could have bugs. I forget D2E. D2S, let's just make sure. D2S. Perfect, D2. So D2S, there's D2E, D2S. Okay, great, great, great. So we've gotten all these out of the way. Next thing is color equal to 1. So instead I'm looking for distance to one of the ending nodes, right? All right, so this should do it. That's good. What else do we have to do? So now we have to populate C2S and C2E. Actually, what we'll do here is we'll do long array C2S equals new long array C. Int I equals 0, I is less than C, I plus plus, C2S of I is equal to long dot max value. All right, and then in here, after this is done, we'll do C2S of I, C2S of color of I is equal to math.min of C2S color of I, and then D2S of I. So this kind of sets the component wise minimums correctly, right? It's kind of do this here too. So long array C2E equals new long array N for int I equals 0, I is less than C, I plus plus, C2E of I equals to long max value. Hopefully this runs in time. I'm like worried about the test examples, but if it doesn't, then we'll leave it to the end to debug that. But C2E is here. And then in here, we also have to update C2E. So C2E of I is equal to, oh wait, hold on. We can just copy this and then reuse the same code. All right, a lot of confusing variable names, so a lot of points for error. So after we do this, then we do for int I equals 0, I is less than C, I plus plus. We have a long and equals 0, or actually long dot max value. C to S of I plus C to E of I. What's wrong with this? Nothing. Print ans. All right, hold on. No. System.out.print line ans. All right, so basically what this code does, this part's very straightforward, right? It just colors everything. And except the reason I color it weirdly like this and this is to make sure that 0 represents the starting part. So the color 0 represents the starting array, color 1 represents the ending array. So that when I get to here, like I can just use 0 and 1, right? Let's see if I actually, yeah, okay. So here, this loop calculates, I use the previous and I update it as I go on and it calculates the closest. So oops, sorry. Say these are the ones here that are the starting nodes. I calculate the closest node in the back direction. So this node's itself, this node itself, this is here, this is here, this is here. And then in the other pass, so in this code here, I calculate the closest starting node in the other direction. So this kind of captures both directions almost, right? And it makes it exhaustive. So here's our code. I think it's ready to get ran on a test. So let's run on this and see what it outputs. Hopefully it like runs. It outputs 2 and then 1. That's weird. That's not correct. Oh, no, it is correct. Okay, cool. For this type of problem, I don't like to debug too hard before I submit it, because you can just submit it and it checks for free, right? So I'll go to solver problem 1. Just see if it works. Hopefully it runs in time. I'm worried that even though the time complexity is optimal, like because I'm using Java, it's slow. Hopefully it's not the case. 2 correct, 3 correct, 4 correct. Okay, it seems like the times are pretty reasonable. That's good. Okay, that one's a little bit high. I have 4 seconds, I think, right? So I should be okay. All right, this is scaring me. 2 seconds is too close to the. Okay, cool. So this is right. Again, the mindset behind this approach, right, is number one, you realize that for this problem, when you're building lines, it's useful to think about components of the graph because you want to build lines between components. So if this is a node of starting value, all these components are like this distance 0 from the start. And it's like distance 0 to go from any node of the component to any other component, right? So when you're connecting this graph, when you're trying to make a path that connects this graph, what you really do is connecting components, right? And once you figure that out, the only hard part is how do you figure this out really quickly? So how do you do it in O of n and not like O of n squared? And the way you do that is you use this kind of trick where you say, okay, I want to find the closest like the closest node to my current node. I'll use 2 sweeps, one in this direction, one in this direction, right? Since this is a live solve, I don't spend as much time as I would like explaining my solution. So I'm sorry if you have any questions, but hopefully that was clear and let's just move on. Yeah. All right, so this is the next easiest problem, in my opinion. So a long grassy patch on a highway, please don't also have input. Okay, thank goodness. It's only 1 test case per. Okay, that's good. You have K grassy patches, and then you have associated tastiness value. And actually, no, hold on. Is this the other problem I thought was hard? I think this is the other problem I thought was hard. Yeah, I don't like this one. Let's go to this one. This is the second easiest, in my opinion. Yes, this is the one about intervals, right? Where you want to check for some value K, whether a sub I plus a sub j is less than K and b sub I plus b sub j. So let's see if there's any intuitive way to like visualize this formula, because having this math here doesn't really help you, because then what are you going to do? Like for every pair of intervals, you can calculate what the K value is. And then for each value of K, you can get the number of intervals that satisfy that K range. Like that's not very helpful. Like that's not very great. We want to avoid doing that as much as possible. So yeah. I mean, for problems like this, I like to just start drawing things out right away. So For every K, you want to calculate. I see. Okay. So if two intervals start at a location, right? So if one interval starts here and the other interval starts here, right? Okay, I think I kind of see how this works. So if one interval starts at location A1, this is like A2, right? You add them up. So this is 2, this is, I don't know, 5, right? So they add them up to 7, right? And then this and this maybe, I don't know, it's like 4, this is 11, and then you add them up and this is 15, right? So for 7 to 15, for those values of K, it's between these two numbers, right? This is just a hard counting problem that we need to think about how to count smarter. So that's how it works, right? I think the most naive way to approach this problem is the following, right? So you have a bunch of intervals here. You loop for all, so for int 1, interval 1, int 2, right? You have an array, right? So KR is our K array. Or actually, we'll call this something different because this is a very vague name. We'll call this like count or answer. Actually, answer is the best way to say this because this is just straight up the answer, right? You get A1 plus A2, you get B1 plus B2, right? You get these values and you look at them and you say, okay, now we have to loop for the values between A1 plus A2 to B1 plus B2, right? Answer at I plus. Like we add this interval into the answer of I, right? This is not very thank you. Sorry, my friend is sitting next to me and she is getting me water. But so for these intervals, you can loop through every pair of intervals and then you can increment the answer. But this is too slow, right? This is what, like O n squared, which like n is equal to 10 to the 5th. So this is like way too slow, right? This might get you like, actually it's even slower than that because you have to loop through every value of K2 and K goes from like 0 to 2m. You know, this is huge. Thank you for the water. You want you want to avoid doing that. So it's like n squared times m, which is way too slow, right? So can we come up with a better way to do this, right? Well, what if we had a table? So this kind of update, first thing I want to talk to you about is this kind of update, right? You want to increment from a range. So you want to, let's think out a way to make this faster. So you want to increment from A1 plus A2 all the way to B1 plus B2, right? This is like a range increment, right? Doing this would require you to typically sweep through all the values between these two numbers and add 1 to everything in between, right? This is very, very slow in my opinion. This is really slow. We don't want to do that. There's a much faster way to do this, and it's called using prefix sums. So what we'll do is, let's actually ground this in some numbers, right? So let's say like we want to increment from 2 to 7. We have an array 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe, right? It goes on, right? So you want to increment from 2 to 7, right? What you could do, you could increment at 2 and then decrement at 8. This seems really weird. Like, hey, why are you doing this? Like, this is a weird way to increment. But the way you kind of justify this is because, well, if I do this, right, and I go through every value, so maybe for 2 to 5 increment, we'll just do from 4 to 6, I also increment, right? So increment 1 at 4 and increment 1 and decrement from 6 plus 1. So this is -1, right? Let's see what happens when we sweep through the array and get the prefix sum, right? So prefix sum is 0, this is 0, this is 1. For 3, it was 0 initially, but since we're doing prefix sums, it's 1, right? For 4, the prefix sum here is equal to 2. So you take whatever value this was and you add 1 to it, and it's 2, right? 5, it's 2, sorry. 6 is 2, 7 is 1, 8 is 1, 9 is 0, right? If you see, wow, this is the same. I messed up somewhere, didn't I? 4 to 6. Oh, okay, sorry. 7 is 1, 8 would be 0. So you see, wow, this is the same as incrementing 1 to this range, incrementing 1 to this range, right? So this is the first like optimization. You take this, instead of making this O of M, you make it O of 1, right? Because you just do this like +1 -1 trick. And then at the end of the day, you sweep through M times. Now instead of like O of n squared times M, it's O of like n squared plus M, right? This is like a prefix sum trick. This is the first trick you need to use. This is really cool. The next trick is, I mean, how do we avoid looping through all the intervals, like every pair of intervals, right? Well, we have to do this. So there's two increments that need to happen, right? There's one increment at A1 plus A2, and there's a decrement at B1 plus B2 plus 1, right? We don't have to do these together for the same interval. What if we do let's think of doing the A1, A2s first, right? So what if I built this array for every value from 0 to M? I tell you the number of intervals that start at that value, right? So maybe M goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Maybe like 2 intervals start here, 3 start here, 5 start here, and then 1 starts at 7, right? So this actually gives me all the information I need to know for A1, A2s, like for the starting locations. This is all information I need, right? Why is this better than doing it for each pairwise interval? Well, instead, so what I actually need to do, so this is like, so this is my information now. What it used to be stored as was this is 2 intervals here, 3 intervals here, 5 intervals here, and then 1 interval here. So for every pair of these 2 intervals, I would add 1 at their added location, right? But instead of doing that, if I have this array, I have a much easier formula. So if I'm looking at 1 plus 3, I'm looking at 4, right? I just have to add like 2 times 3 to this location instead of adding 1 like 6 times, right? And this is a lot faster because instead of doing 6 different additions, I just do 1 multiplication and 1 addition, right? So I still have to iterate between every pair of starting locations, but the number of starting locations is much smaller than the number of starting intervals. Intervals is 10 to the 5th, n is 10 to the 5th, and then M is like 5,000, I think, right? So we can do an O of M squared update. So looking through every possible pair of starting locations, and we do this like plus a times B operation, right? And then for the ending location, we do the same exact thing. It's like you subtract a times B from the value of like I plus J plus 1, right? And then after you do this, you'll get this like answer like array. And then you'll have to run through and do prefix sum, right? And then you're done. So let's just recap the algorithm in the stages it has, right? So stage 1, for every I get number of intervals, start and end at I, right? Then the second step is for every pair A1, A2, compute A1 plus A2, and then do array of A1 plus A2 plus or equals n of A1 times n of A2, right? Maybe this is ns, ns, right? And then the third step is for every pair B1, B2, do array of B1 plus B2 plus 1 minus equals n, yeah, n end, not like number of ending intervals, maybe B1 times n end of B2. Let's just run this on an example case to make sure this algorithm is sound for the, because this would be really bad if it wasn't sound for the input case, right? So this one right here. Oh, this is very small, so maybe it's not super useful, but we'll still check it. So it's 2, 5. So the intervals can range from 0 to M. Oh, I guess we have to use M plus 1 then if it's 0 to M inclusive. So if M is 5, it goes 0, 1, 2, 3, 4, 5. So this first interval, 1, 3, right? What do we do here? We look at 1, we look at 3, and we say this is NS, this is NE, right? So NS at, this is what, 1, 1, 3, 2, 5. So NS of 1 is 1, NS NE at 5 is 1. Oh, sorry, any at 3 is 1, and then n1 at 2 is 1, and then this is here, and then everything else is 0, right? This is just filling out the interval information. So for this one, you can verify that the only oh, and then we're missing one. Yeah. So you can verify the only thing is, so you have to look at like interval starting at 1 times interval starting at 1, right? Plus interval starting at 2, interval starting at 1. So I forgot actually a case of this, right? So it's not just every pair A1, A2. This is if they're not equal. If they are equal, you just do A1, because we're counting pairs of intervals, right? Ordered pairs, okay. So if they're not equal, what you do is you say A1, if it's like checking A1 against A1, so like 2 intervals from the same bucket, you do A1 times A1 minus 1 over 2. Like that's how much you add to like 2 times A1. So this is something else we'll keep in mind and we'll do, but we'll talk about that when we code. So for the input case, I think this is correct, right? So at bin 2, you add 1, and at bin 8, you add 1. So from 2 to 8, it's 1, and then for everything else, it's 0. So is that correct? Oh, that's totally not correct. Wait, hold on. What? Hmm. I think I'm misunderstanding the problem. Let me just check. Okay, so you have intervals, right? And intervals, each interval starts position and subposition. Play a game, Bessie chooses interval, her cousin Elsie chooses some other interval. Say J. This could be the possible. Oh, it could be the same as Bessie's interval. I see. Okay. Oh, okay. So, oh, and this is ordered. Okay. The multiplication is slightly different than what I thought. Okay. So Elsie could actually choose the same interval that Bessie chooses as well. I see. Okay. What does that mean? So I still have this. I think this table is still useful. So this NS and E. So, but we have to use it in a different way now. So the math is slightly different from this approach. So I guess to modify the naive algorithm, do we still have that written down? No, we don't. The naive algorithm goes, okay, hold on, I see. Ah, okay. So it's slightly different than what I thought. So I thought Elsie had to choose a different interval that's not Bessie's interval. And I thought it was for unordered pairs. So the math is slightly different, but I think the approach is still like valid. Let me just erase this real quick. Let me try to get the right answer. So I should read the problem carefully because there was a very real chance that I misread the problem. I solved a completely different problem. Thankfully, I misread it and I solved a very similar problem that I think is the similar solution type. but that could have been a real disaster. So I'm glad it didn't happen. Okay, so step one is you do the same again, except here's the thing, right? You iterate through every A1, A2, right? For A1, A2, you have to make sure, even if they're equal, it's fine, right? So A1 can equal A2. Like that's something that I completely misremembered. But if A1 does not equal A2, so first you do array, you access array of A1 plus A2, and then you plus or equals to. Instead of this being A1 times A2 in different cases for whether the same one, it's actually going to always be, so I think it's typically, let me see. Yeah, okay. It's typically just going to be 2 times A1 times A2. The only other case is if they're the equal. If they're equal, it's plus equal to A1 times A2. And the reason why is because if they're equal, you can't, so if they're not equal, you select one, you select the other one, and then you can switch them. But if they're from the same bin, you select one, you select the other one, you can no longer like switch them and mix match. So for them being the same, it's A1 times A2. For them being different, it's A1 times A2. It's 2 times A1 times A2. Yeah. And then for, I'm sorry, my parents are home. So if you hear a little bit of noise in the background, it's totally fine. Just focus on the problem. So that's how you do the what's it called, the A1, A2. And then for B1, B2, you update array of B1 plus B2 plus 1. And then you do subtract equal to the same value. So 2 times B1, B2. So you, yeah, do the similar type of logic. So let's code this actually now. I think it's kind of pointless beating this horse while it's dead. So we could just solve the problem, right? I'm really happy the input's a lot easier for us to work with. The input for the other problem was just the worst. I don't like when they have like this whole t-test thing. It's just an excuse for them to, I'm sorry. I just, coding with Java is very difficult in competitive programming because every second matters. You just get a very large slowdown from using that. So let's go through this. Let's get rid of this thing. This thing. All right. So you read in N and M as you did before, and you also have this interval array. So we will actually bin them right away. So we'll do static int array and number of starts and then number of ends. So let's keep track of our intervals calculations, right? And we also need to keep track of our answer. So we'll just do this. This is the tricky part with buffered reader. So you have to do, how do I do this in this problem? In dot read line dot split, and then we'll split on the space token. And then we'll do n equals integer parse int imp of 0, m equals integer parse int imp of 1. Let me get some water real quick before going on and just like getting dry. So give me a second. I'll All right. Hey guys, sorry about that. Okay, so let's read the input in. We get this, and then we'll do for int I equals 0, I is less than m, I plus plus. Sorry, some of my friends in the background are talking, but just again, focus on the context. We got this. String, we'll just do this. Input equals. I think there's a better way to do this, but I mean, I'm not super experienced in coding at this point in using buffer reader. So let's see, we'll do A equals integer.parseInt input at 0. We'll actually make it a long array and make our math easier, not overflow. So this is actually going to be n plus 1. And this will also be n plus 1. Yeah. Input at 0. So we'll do int b equals integer dot 1. Okay. So these are the actual endpoints, the interval. We want to actually change things to their. We want to add to their bucket. So we'll do ns of a plus plus, and then ns of b plus plus. Cool. Okay. So now we're done with that. So all of our buckets are collected. We'll make a new long array, ants. What is this? 2 times m? 2 times m plus 1. Okay, 2 times m plus 1, because it's from 0 to m inclusive, right? So for int I equals 0, I is less than n, I plus. Well, this is actually going to be to m, I plus plus. For int j, so here's the tricky part. For int j equals I plus 1, j is less than or equal to m. Actually, we can do this. Wait, let me think. Yeah, okay. We can do for int j equals 0, j is less than or equal to m, j plus plus. So what this kind of does is it loops through every pair of buckets, right? So it's as if to choose the intervals, Bessie picks an interval, picks a number, Elsie picks an interval, picks a number. So like picks a so instead of just choosing, so it's supposed to be Elsie chooses interval, Bessie chooses interval, right? So instead of doing that, what we'll do is Elsie chooses the bucket, chooses an interval in that bucket, Bessie chooses the bucket, chooses an interval in that bucket, right? So we'll just do ants of I plus j plus or equals ns of I times ns of j, right? And then we have to do the ending. So ants of I plus j plus 1 minus equals ne of I times ne of j. So that settles that. And at the end of the day, we have to do this for int I equals 0, I is less than or equal to 2 times m, I plus plus. We'll do long total equals 0, tot plus or equals answer of I, and then we'll system.println total. And that should work. Let's run this real quick to test it. This example. It's time limit exceeding somehow. I think it's probably just waiting for input. What did I do wrong? Oh, I read n and I read m, and then I loop from this to be n, the number of intervals. Yeah, that's what I'm doing wrong. Okay. Index 11 out of bounds for string 11 on line 25. So I go line 25 here. Okay, so this can be a definite problem. How do I resolve this? Oh, this is a simple way to resolve it. Yeah, here we go. Again. Geez, this is very wildly away from. Did I do? this properly? I did. This is huge. It blows up way too fast. 0, 0, 1, 3 looks promising, and then 6. I don't think that's working properly. It should be 4 only. What could be going wrong here? So let's just sanity check this. That print line in S. Does that even work? I don't think this works actually. So that print line. I guess we'll just do this for int I equals 0, I is less than n x plus, and then system dot out dot print line. No. So equal to, what's the size of ns and n plus 1 dot print. Oh, this is m actually. So that print line and s of I plus 0 plus an e of I, and then out that print line. Oh no, hold on. So that's good. It'll just print them all out. This is slightly weird, but I'll just print them all out side by side. So just to take a look. Oh wait, sorry, that's why. Because they're adding. I forgot to add to ne. I only add to ns. Yeah. Okay. So now we'll run. And then yeah, that looks right, doesn't it? Cool. Okay. So I think I'm just gonna submit this and see if it works. Hopefully it does. And I won't have to debug anymore. But if it doesn't, then we'll have to come up with harder case to debug. So this one should run quickly, I think. I'm not as worried about time length for this one. It should be pretty fast. Yeah. Well, these are the first few inputs. Let's see. Wow, a lot of cases for this problem. 13. 15. 17. Okay. There's like 50. There better not be like 50 cases. How many cases? Oh, there's only 20. Okay. So we're almost done. Yay. Okay. Nice. Good solve. So now let's do the last problem. I'm gonna take a break right now to go to the bathroom. Just advice for solving contests. I know that the time crunch is real sometimes, and for me solving it feels a little bit lax because like a lot of these problems are like I'm doing it at a very brisk pace, but in general you might feel time crunched. I think even then it's important to take breaks because a lot of times if I focus on concepts for way too long, I get into this mindset where I'm not able to think correctly. Like I just feel very like tired and stuff like that. So it's a time contest, yes, but go to the bathroom, like walk around, like don't think about problems sitting down at your desk. I have to do this because I'm recording for you guys, but if I were actually doing a contest, it'd be a lot more of me like pacing around the room and muttering to myself. Just like get some variety. So you're not just staring at the computer screen and like getting like really like honed into that and not like being creative, because a lot of these problems are about creativity. So I'm gonna go to the bathroom and yeah, take a break. In general, you should take All right. Hey, everybody. So let's take a look at this problem, the closest cow wins problem. This intuitively to me is probably going to be a little more annoying. It's one of these like, oh, like we have to fight a strategy problem. Again, I like to draw things out. It just helps me visualize things better. And I think it's a really useful like way to approach these types of problems, right? Because this all comes down to approach. I think it comes down to having an insight about the actual like problem itself. And that doesn't come from just like trying to turn this into like a really easy, like turn this really simply into another problem. So let's see, tastiness patches. I think so. Let's just draw stuff out. Yeah. Let's say if this taste, let's draw these tastiness patches of the height of how tasty they are. This is a one-dimensional array, right? And then you have like these bad cows. Situated across the plane, right? Observation one I want to make is you're always going to put your cows either to the immediate, because you can put them in fractional places, right? You need to know the score you get, right? You want to put your cows like to the immediate right or left of Farmer Noge's cows. So here's the idea why, right? You want to put your cows places, we'll make our cows blue. We want to put our cows places to win the max score, right? So let's say I put my cow here and it wins like this score, right? I could just as easily choose to put like, so I'm trying to win this score, right? I could just as easily like, what am I taking this from? I'm taking it from this. Actually, let me think. Is this true? Maybe it's not true. Let me think. So all this is about trying to make like observations that make the problem a little bit easier. So let's just kind of toy around for a little bit. This is our number line. We have a bunch of cows here. Then Farmer Noge has cows like, the closest cow gets the patch, right? Yeah, I guess this is a counterexample, right? Because if I put my cow like here, it's kind of splitting this patch with this guy. If I put him here, it's kind of splitting it with this guy, right? So maybe I won't put my cows. Maybe it's better for me to put my cows like if the thing is like this, right? If maybe the cow tastiness values are located like a lot of good ones in the middle. Maybe it's just for me to put it here and collect like these cows, right? Maybe that's the best thing I can do. What kind of solution does this problem have? I think it's easy. It's important to look at it. Not important, sorry. I think it might be good to look at it this way, right? If I have cows like here, or sorry, hold on. If I have a number line, right? There's some bounds in the number line location. Oh no, there's not. Tastiness. Wait, no, hold on. Is there? No, all these locations are distinct integers in the range of 0 to 10 to the 9th. Yeah, okay. So farmer Noja's cows are here. If I put my cow here, right, it takes everything from here to here. Let me just make sure I'm reading this problem properly, because maybe I'm like, I want to see if I can, maybe I'm not understanding this properly. I'm not really making a lot of progress so far. But oh, you know what? No, maybe wait, hold on. Let me make sure I'm reading this correctly just to be careful. But okay, so there's K grassy patches, each pass located position PI and associated taste value TI. Farmer John's nemesis situated M cows allocations F1 through FM. All locations distinct integers in a certain range. You need to pick N locations for the cows to be located. These must be distinct from those already occupied by the cows, but possible Farmer John to place his cows at the same locations as grassy patches. But it is possible Farmer John to place his cows at the same locations as grassy patches. Okay. There are two cows from rival farms equally close to the patch, then Farmer Noach claims the patch. Okay. So with one cow, keep in mind, so it looks kind of weird. Like if I place this cow here, my interval is like this, right? Put the cow here, it's like here. Actually, oh no, I erased all my pen. Oh no. Say I'm gonna just do this in black. So these are Farmer Noach's cows. If I put a cow somewhere here, right? I'm taking up maybe this interval to like this interval, right? The length of my interval is always going to be like this. This is like length L, right? It's going to be L over 2, right? You can kind of convince yourself of this by looking at this diagram, but kind of that's the same idea, right? Like if you if I put my interval in right dab smack in the middle, if I put my interval like sorry, let me just look at this. If I put my interval like on the way end here, it gets like this half, right? Which is L over 2. If I put it on the way end here, it gets this L over 2 half, right? If I put it in the middle, it gets like L over 4 and L over 4, which is L over 2 in the middle. And you can kind of slide it along here. So it's kind of like this, right? Pen color black. Okay. So you can partition this grid into this intervals between Farmer Noach's cows, right? So there's like this guy here, this guy here, guy here, this guy here, this guy here, right? For one cow, for the price of one of my cows, right? I can place the cow here and get basically this entire region. Put a cow here and get this entire region, right? But for the region sandwiched between two Farmer Noach's cows, if I put two cows in that region, if I put like two cows here, I can get the entire region Or I can put one cow down. I can put one cow down, right? And get like some half of this region, right? Like half length of this region. The first trick is to figure out like what that value is. I wonder if the answer is just greedy. Like you put the cow in the place to get the most. I think it might be a greedy problem where, so okay, for every, these reasons are easy, right? If you put, geez, all these colors are tripping me up. So this is the interval, right? Here's Farmer Noge's cows. How many regions are there? There's 1, 2, 3, 4, 5, 6 regions, right? These two regions, if you put like the n regions, if you put a cow here, it gains you the score of like plus whatever like total number of fields are in this region. Because you just put it really close to Farmer Noge's cow and you get this entire region here, right? Similarly, for this one, you also have to, it's a similar kind of logic, right? Now for each of these regions, right? Put one cow in this region, you make the max half. I call this the max half. What's the max half? So if you look at this region up close, there might be like gains, like profits here, right? You want to find out, this is a window of size L/2. If this is a size L, this is a window of size L/2. You want to take this window and you want to like slide it over, like take this window, like slide it over and find the maximum score from that window, right? That's how much you'll gain by putting one cow optimally in this region. Putting two cows optimally in that region, right? If you put two cows in this region, you get the entire score of the entire region, right? So I actually argue that the max scoring region here is greater than half of the whole region, right? You can kind of see that for yourself. I mean, just reason out, if I'm placing this optimally, it's going to be better than just half the whole region. Another way to think about this is if you have this entire region here from here to here, looking at this L/2 region and this L/2 region particularly, right? They both sum to the whole region, right? Additionally, one of them is greater than the other. So if you take a maximum one, it's greater than or equal to half of the whole region, right? So when you take, so if you look at this, right? If we write out for every region, like, so if this is like 1, 2, 3, 4, 5, you have 6 regions, right? If you can write out each region, the gains, right? You'll have something like this. Maybe this is like you get 40 gain from putting a cow in this region, right? You get 30 gain and then 20 gain, right? So maybe this has a total score of 50. Maybe this is like 10 gain, 5 gain. This is like 40 gain, 30 gain, 20 gain. 10 gain, and then this is 30 gain. So what this kind of says is like, here's the gain. The gain I write here is like, if I put a cow in this region optimally, I'll get 40 points, right? If I put a cow in this region, I'll get 30 points. If I put another cow in this region, I'll get 20 points. That's what it kind of says. So 20 additional points to that 30 points. So this is a total, maybe this is a total like 50 region, and putting one cow here, I get 30 from that like L/2 interval. And then if I put two cows, I get the entire interval of length 20, right? So the top number is always going to be less than the bottom number from this property we said before, where the max score is always greater than or equal to half of the whole. So what does this mean? This means we can actually behave greedily. So let me think. Ooh, sorry, didn't mean to do that. Actually, we can just make this consistent. This can be like 0, right? You have no additional gain for putting another cow there. So yeah, so how this works, we can actually behave greedily. We look at these, so we can't just take from the top right away. We also don't want to do that because it's always less than a value at the bottom. So we can behave greedily. Let's say we want to pick the top 5. We want to pick 40, and then we'll choose this 40 maybe, and then we'll choose this 30, and then this 30, and then we'll pick like this 30, right? And that's the configuration to put cows to get the max score. So put 1 cow here, we maybe put 1 cow like here, right? Hold on, let me just describe this, write this in black ink. So if this is the maximum score, it's the equivalent of kind of doing this, right? Put a cow here, put a cow maybe here. Since we chose 2 cows, we put 1 here and here to get this entire region, and then 30, put 1 cow here, right? This would be the answer for this configuration. But yeah, so there's 2 problems here. Step 1, for each like region between these 2 cows, for each region between 2 cows, we want to kind of calculate the best half length, and additionally we want to calculate the total sum. Yeah, so that's our task, right? Calculate the best half length, calculate the total sum. What are we getting in this? Is this input sorted? Oh, is it sorted? It's not sorted. That's annoying. Hold on, wait. Let me make sure because this input looks sorted. So I'm just being hopeful here. No, it's not sorted. So we'll have to sort these. So for each like interval between 2 cows, we want to compute the best half length, the total sum, right? For the interval like above all the cows, we should consider like the best half length as equal to the total sum. So yeah, this is a good way to do this. Okay. Primary nodes locations. All right, okay, I think we're prepared to do this problem now. So how do we, so after we get this amount, then we just greedily select. So we have an array, we have this array, right? So the second step, step 2 of this algorithm is, step 1 is you find the best half-length total sum, right? Step 2 is you take this information and then you add them all to priority queue. So you first add all these to priority queue, right? You pick the best one, and when you pick the best one, if it represents a half length, you add the total sum into the priority queue. So you now enable us to take from 30, right? So you use a priority queue to do this. Use priority queue to do greedy, right? Use PQ to do greedy. Actually, do you even need to do that? I don't think you need to do greedy because the only, sorry, I don't think you need to use a PQ because the only reason you need to use a priority queue is to kind of like, you want to kind of simulate this process of picking the like, you want to simulate this process of like, okay, if I choose like this, I'll have unlocked this one, right? So you don't want to be able to take 30 before you take 40. But if I just sort all these values and pick the n greatest values, I think that's fine because why would I ever pick this before picking this, right? So I think I've actually just sort them. So instead of doing this, sort plus greedy is good enough, right? So the tricky part is calculating this best half length and total sum. So we will work on that. This is a little bit tricky. You have to do sorting. I'm not great at it, so the implementation is going to be like a little bit of a pain, but you know, we're almost done this contest. Let's just finish strong. Import java.util.asterisk, import java.io.asterisk. Wow, I'm like brain farting on how to do the input. The exception. Yeah, okay, here we go. What is this? So what NM and K, M and N. So K is the number of grass patches, M is the total farmer noticed cows, and N is what you need to have. So I'm gonna make a class called grassy, and I'll do do I need to do this? Can you sort 2D int array in Java? Okay, you know what? I'll just try it and see if it works. All right, static int array grassy, static int array knowledge, like that. Is that how you spell knowledge? Yeah. So that's the grassy cows, that's the knowledge cows, right? All right, okay. So again, we have to use buffer reader because I think this input's a little bit gonna be a little bit hard for this problem. Just want to make sure that we don't run into input problems, right? Buffer reader n equals that, right? And then we have to do, sorry, new. And then we have to do in dot read line dot split by the space character. And then k equals integer. That's why I like scanner so much better. Like this is just such a pain to do. It's not, I'm tempted to use scanner, but I should set good examples and not use scanner. 0. Okay. So we also have to do this grassy. Maybe I'll do long array. Yeah, I'll do long just to make our lives easier. Do long node. Grassy equals new long. So this is of size k by 2. And then node is of size m by m. Yeah. Then so first you get the location, then you get the tastiness, right? to get P of I and then T of I. Cool. Long dot parse long. Imp of 0. Grassy of I1 equals long dot parse long. What's wrong? What's wrong with this thing? This is just take some time to update. Okay. Okay, so that's for the grassy cows, and then for int I equals 0, I is less than k, I plus plus. Oh, please don't tell me. Okay, we'll see if this works. Yeah. And then we can do. Okay, whatever. Node like this equals node of I is equal to long dot parse long imp of 0. In the future, I think I'll use C++. This is getting a little bit tedious. Because back in my day when I used to code in back when I coded competitive programming, I used to use Java and I used to use this class called FastScanner. That was kind of like just like all the people who did Java kind of use the same FastScanner class, but you're not allowed to use templates now. So yeah, kind of it's rough. So now can't use FastScanner. So I think C++ is probably the best. It's like honestly at this point the best language for competitive programming. Java is better debugging, but it's kind of marginal. Like C++ is so much faster that it's probably worth it to do C++. All right. So the first step, like we said, is to get the half lengths, right? So you have to sort them both. So arrays.sort node. That'll just work, right? And then we'll just do arrays.sort. And then we'll have to sort with the custom comparator. So we have to sort grassy. Wait, okay, I just try to autofill this in. Yeah, this is what we want. No, it doesn't fill in the thing. Okay. In VS Code it does. So I mean, sorry, in IntelliJ it does. Grassy, no. Does it just do the entire thing? No, it doesn't. No, that's not what I want. Comparator of int array. Like that, right? I think I need to do this. What is this? What's the issue with this? Hello? It's an error message. I know what comparator is. Public int compare. Is this what you have to do? This is how you sort using specific stuff. You might have to do like. No, I don't know if this is necessary. What is this thing? Is that not how you do it? Is it like this? Let me Google this up real quick. Custom comparator Java. Oh, I can do that. That's annoying though. Oh, I can do this, yeah. Oh, is it just this? Oh, that's all you gotta do. What is this? What's the issue with this guy? Okay. Okay, all right, here we go. We're in business. I still got it. I don't need to Google it up. Okay, I still remember this. This is like a memory from the deep recess of my mind. Return, let's do return 0. It should go. Yes, okay, perfect. Okay. So you want to return long dot compare A of 0 with B of 0. All right, yeah. Oh wait, sorry, return long dot compare A of 0, B of 0. Perfect. Okay, so can we condense this so we don't have to look at this ugly thing? Yeah, okay. Ooh, wait, that's not correct. Testing code and then use, yes, perfect. Okay. So now we sort both nodes and we sort grassy, right? Here's the way we're gonna get this half length thing, right? What we're actually gonna do is this. Let's zoom into the specific region we care about the half length thing for. Here are the tasty patches inside this region, right? We're gonna iterate. So we have a pointer that starts at the first safety patch, the first not safety patch, the first tasty patch, right? And here's this interval, right? We look, so we keep track of this end distance, right? This end point. We set this equal to previous. So L we set to be x of I minus x of I minus 1, right? This sum is, you can go through this for every, while the integer is like less than x, you loop through it and you say, add this to the list, add this to the sum, and then also we keep track of the running current sum. So maybe this is L2, right? So for here, it's like this plus this. And then, oh, you keep track of a lagging pointer. Oh, this is gonna be really annoying. Is there any better way to do this? I don't think so. I think this is the only way to do this. So yeah. We could run a forward backward sweep for every. No, see, that's too slow now. That might be in squared. Yeah, I think the best way to do this is just you keep track of one pointer. This is, maybe this is like call this like P1, and then P1 and P2 start off the same, right? We increment P2 while we can, and if we can increment P2, we keep incrementing it. Invitation is getting a little bit hazy for me, but so while the distance between P1 and P2 is less than L1, you can increment P. So you increment P2. So you first start with P2 here. Update, like you say, for this pair P1, P2, calculate, get the sum equals whatever. You have the total sum, right? That you just keep equal to something. For this P2, P2, you update this sum, you update the total sum, and then what you're gonna do is you're gonna move P2 forward. You step P2 like forward. Geez, this is really annoying. So you step it forward and then you iterate, you make sure that if P1 minus P2, so while like P1, P2 minus P1 is greater than L over 2, because it can only be of size L over 2 exactly. Wait, let me think. Is it greater than or greater than equal to? Because that logic is important as well. Get the endpoints, you don't get the endpoints. No, it's greater than or equal to, because at the endpoints, farmer node takes the cow, actually. So it's greater than or equal to, well, it's greater than or equal to L over 2. Yeah, if they're just distance, you can only pick one if they're just distance L over 2 apart, because try to put it right smack at where it should be, then the endpoints are equidistant, and then the endpoints get, yeah, okay. So whilst listening to 2 part, you do P1 plus plus, you update the sum, the total you can keep the same, and you just add the total, yeah. So it'll make more sense when I write some code. So they're sorted, which is the important part, right? I plus plus. Jeez, this is a brutal program. I think we're actually gonna do is we're gonna give Farmer Noj a ghost cow that extends to, yeah, okay, we're gonna give Farmer Noj a ghost cow that extends to a really ridiculous height in the, we're gonna act like, just for ease of coding, we're gonna give Farmer Noj like a cow all the way here. Sorry, all the way here. Because it shouldn't affect us, right? L. For safety, it'll be like really, really far away. So this is M is this plus 1. Can I do that? No, I can't do that. Gains equals. Okay. This is what I like to use for like huge infinity values. Like we'll just like, because the reason why is because long max value is really close to the overflow point. So we don't want it to overflow if we just do things with it. So over 2 should be good for us. So going back to this, right? So from 0 through M, if I equals, so L, if L, if I equals 0, L equals, I don't know, just something huge, ridiculous number. Else L is equal to Noj at I. Okay, so that's L. So long max half. So am I consistent with max half sum? 0 long tote sum. So equals 0. So tote sum is the total sum in the region. Max half sum is the max sum of the half L over 2 sections in the region, right? So while P2, is less than, so while grassy at P2, 0, so we're gonna try to iterate through the grassy patches and just get grassy patches. So this is node cow 1, node cow 2. We're gonna make sure the grassy patches are between the two cows. Someone just came home, I think. Okay, sorry. We want to make sure our cows are within these grassy patches here. So we'll check whether grassy at P2, 0. We want to make sure that it is less than node at I. If it's greater than, it can't be equal to, because farmer node can't put cows on grassy patches. So if it's less than node of I, then it's good, right? But if it's greater than, we want to stop. We don't want to do it anymore, but yeah, okay. And at the end of this, we want to do P1 equal P2. We want to like shift them up to each other. So oh, I see how we're gonna do this. Okay, plus or equal to grassy at P2, 1. Cur sum plus or equal to grassy at P2, 1. And then we'll do P2 plus plus, and then we'll do while grassy at P1, 0. So while grassy of P2, 0. So the distance between the beginning and the end, right? We want to make sure this distance, 2 times this distance, right, is less than, wait, hold on. Oh wait, so this distance, if 2 times distance is greater than or equal to L. So if we take the distance between the two things and then we multiply by, if it's greater than or equal to 2, if it's greater than or equal to L over 2, then we have to shift, we do tote sum minus equal to grassy of P1, 1, and then we'll do P1 plus plus, shifts P1 upwards, right? And then we want to iterate this for all things. At the end of this, we'll get to, wait, so grassy was in, no. P2 is less than M, right? No, K. We need to get our variable straight. So this is M. This is M, this is K, right? Wait, this is a little bit weird. Hold on, something, I coded this weirdly. What if I just do this? Oh, okay, I see, okay. So this is not tote sum, this is cur sum. And then this is max. That's not max half sum and then cur sum. And then we do P2 plus plus. Yeah, okay, that should work. I think that should work for everything. So for the endpoints, the max cur sum should max half sum. You'll never hit this condition, so P1 will never be incremented. So tote sum and cur sum are always going to be equal, and max half sum will equal cur sum. So we'll do grassy. We'll do gains dot add Okay, so this is important. So gains is the important thing to write. And then at the end of the day, what we'll want to do is arrays.sort gains for int I equals gains.length. Oh, gains.size, sorry. That's one. What is wrong with this? Oh, it's probably just I greater than or equal to min of 0. Oh wait, no, max of 0 and gains.size minus. So n is the number of cows you can place, right? N, I think. I minus. Okay, what's wrong with all this? Oh, this is math.max. What is wrong with arrays.sort gains? Ah, this is collections.sort gains. It's big array list, sort it. Ah, should I use array? This will be faster. Yeah. Long array gains equals 2 times m. And we'll do gains of 2 times I equals max half sum. And then we'll do gains of 2 times I plus 1 is equal to tote sum minus max half sum. And then we'll do arrays.sort again. This is going to be, if this is the death of me, this is the death of me, because their n is 2 to the 5th, m is 2 to the 5th. So we're sorting 4 to the 5th, 4 times 10 to the 5th, which is too big. It's really big in my opinion. I'm kind of terrified. So, okay, gains dot length minus n. If n is equal to 1, it checks if, yeah, okay, so I think this should work, right? Long ends equal 0, ends plus or equal to gains of I, system that print line. All right, so we're gonna debug this. It definitely won't be right. If it's right, I'll be so surprised. We'll debug this and then figure out the bugs in it, and then yeah, we'll see. But for a sec, I need to just get my more water. So give me 1 second. I'll be right All right, okay, let's debug. I think what I'm gonna do is actually print out the gains array. Wait, hold on, let's do this. Actually, well, no, the gains array is not the most useful thing to print out. Dot print line max half sum plus total sum minus max half sum. All right, let's print out what we should be getting for this problem. Let's just do the example case using our algorithm, right? We should have done this way earlier. This is a mistake that I made. But we should be doing this. Oh, okay, testing. Okay. So we should have done this a lot earlier. Wait, testing mic. Okay, hopefully the audio is working. Testing. Okay, testing. Yeah, hold on. Speaking. Okay. So we should test this a lot earlier. Right? I shouldn't have saved it until now, but I mean, better late than never. So we'll just test this right now. Here's the number line. Here's the number line. Farmer no just cows was situated at 2, 3, 5, 7, 11. So 2, 3, 5, 7, 11. Yeah. So one cow at. Why did I draw an X here and then everything else I wrote it as a line? These are farmer no just cows, right? The grassy pastures are, we'll draw them in green. 0, 4, 0, 4, 8, 10, 12, 13. 0, 4, 8, 10, 12, 13. With weights 4, 6, 10, 8. Jeez, this is a lot. 12, 14. And we have 2 cows can put down to get the max. Okay, so what we should have for these half lengths are, this should be 4. Oh, sorry, hold on. Don't resolve it. This should be 4, 0. So half length 4, because of if you put 1 here, you can get this. It's a corner case, it's only elements, right? And then full length 0, because you get no other gains after you get the 4. This should be half length 6, full length 6. So if you put a half length right here on top of 6, you collect the 6. Otherwise, oh, full length should be 0. Oh yeah, so 4, 0, 6, 0. It should be what you get, right? Because we're doing total sum minus, yeah, okay. This should be 0, 0. This should be, I don't think you can collect both. I think you can only collect 1. Because to collect both, this is a difference of 8, 10, 2, 4. Yeah. So you should get something like 10, 8. And then this, you should get 26 and then 0. And that's the correct way to approach this input case. Let's see if we get that when we solve the algorithm. So problem 3.java, we're gonna run this. Okay, index out of bounds, index 6, length 42. So here. Oh, okay, wait, hold on. I just reversed this order. Try that same issue as I had before, where if you do this check after, it doesn't. If you do check before, it doesn't work. You have to do it after, because this will cause this to short circuit and evaluate. So yeah. Oh, sorry. Ah, geez, I messed that up. So I get 36, and then I get 4000060. Wait, sorry. Oh, there's that space here that I even forgot to see. So 4000600. 8, 10, yeah, 10, 8, 0.60. Yeah, perfect. Okay, that's. Oh, drop my stylus. worked for this input. Let's see if it works in general. So we will take out this print statement and then submit. If this works, then we're very happy. If this doesn't work, we're very sad because I think this is gonna be a really hard problem to debug. It's really conceptual. So I'm really worried if this doesn't work. It's a good sign. It's a bad sign. These are so slow. Okay. It shouldn't be. I can't think of many other ways to speed this up. It's pretty lean down in my opinion. Oh my goodness, how many tests are there? Oh my goodness, this is terrifying. Probably 20 tests. Please don't, because oh thank goodness. There's more. Okay. The speed seems dubious. Oh, thank God. Okay. Yes, that's a solution for this problem. I'm so surprised this worked first try, but the idea here is kind of just like you want to use the hardest part is, so the one hardest part is like, hey, like you have this problem with like farmer knows just cows here. How do you solve this problem? You realize like, okay, so if I put one cow like in this, you can look at this problem as separate regions, right? If I put one cow in this region, it collects like this half length here, you know, and this is like, so one cow collects a half length, one, and then two cows collects the full length, and the half length will always be greater. So you have the structure of like, put one cow in this region, you'll get this amount, two cows get this amount, right? So for every region, kind of boil it down to this. When you get down to this problem, the hard part is realizing this is greedy, right? So realizing that, okay, the best way to select this is just to pick the maximum values, right? And after you do that, you'll solve this problem. This part's not terrible. The really bad part implementation wise is realizing like, how do you calculate this half length here? Well, I'm going to go into that more in detail here. So have no just cows on either side, right? Here are some grassy patches. I want to check. So if I take an L, I want to take an L/2 region and kind of like slide it along this entire like part, right? So slide it along this way almost, right? This is not very easy to do in practice. A lot of values between these two regions. What you want to do instead is like say, what if the L/2 region ended here? What if it ended here? Because again, we don't care about this region, right? This region is the same as like ending it off here. So what if it ended here? What if it ended here, right? And doing this for every region. And the way you calculate this is this is like a 2-pointer approach where you iterate forward for the end pointer here, you iterate 1, 1. And this back pointer, you update it. So if you say you iterate from your back pointer is here and your start pointer is here, right? You go to back pointer here, start pointer here. Now this is too long of a region. This length is greater than L/2. So what you do now is you take this back pointer, you move it up once. Now this is P1 and this is P2 instead. And you kind of do this for the entire length, and you kind of repeat this for all the lengths. This logic is kind of in here. It's a little bit hard to understand this like 2-pointering, but that's the way I think to beat this problem. I don't know if there's any other solution I'm missing, but yeah. So yeah, I think you are good. So I will take the in-contest promotion and I'll see you guys in the other contest. Have a great rest of your day.